All right, so today we're going to do acids and bases. Not just acids, but acids and bases. What is this thing? Tell me what it is.
Gargoyle.
It is not a gargoyle.
That's the remake of Godzilla.
The remake of Godzilla. No.
Acid corrosion.
That is right. He is a grotesque. A gargoyle is a water spout. A gargoyle is a water spout. For example, if you're ever at the National Cathedral, they have really neat gargoyles all around it. There's even a Darth Vader gargoyle.
I've seen that.
That is cool. A gargoyle is a water spout. It's where water comes out of the mouth. Okay, a grotesque is a statue whose job is to ward off evil spirits. That reminds me of one of my favorite cartoon shows of back when I was a younger man, but it was completely misnamed. It was Gargoyles. That was a cool show. It starred a lot of old, former Star Trek voice actors. So, but what should they have called it? Grotesques, which I don't think would have been as good. All right. So what's wrong with this gargoyle?
It's got acid rain.
It has acid erosion right there from acid rain. No, because all rain is acidic. Actually, if rain was not acidic, then life as we know it would not exist, because we count on rain being acidic in order to dissolve minerals that normally cannot be dissolved in water.
Take that out.
And those minerals get into the ground and provide plant food. So really, it is a misnomer to say acid rain. You should be saying excessively acidic rain, or extremely acidic rain, or very acidic rain. So very acidic rain damaged this grotesque. I almost said it, grotesque. This grotesque. And it probably was made hundreds and hundreds of years ago, but it probably has encountered more damage in the last few years than in most of its existence. Thanks to the Industrial Revolution. We'll talk more about very acidic rain later. I can identify a substance as an acid or base by its properties, including pH, reactivity, dissociation in water, taste, feel, and chemical formula. What are some ways in which acids affect our lives? Well, it's what gives lemons and Sour Patch Kids and sour candies their sour taste. It helps us digest food. I have probably still in my stomach the remains of today's lunch, which was a hibachi burger. Ooh, it was good with plenty of French fries. Oh, that was good. The acid in my stomach is going to town, trying to digest that hamburger into smaller bits. If my pyloric sphincter, my cardiac sphincter, if my cardiac sphincter is not working properly, then it will allow acid to shoot up my esophagus and give me heartburn. Cardiac sphincter is what controls the little trap door that opens to allow food to come out and closes so that the gastric juices, the hydrochloric acid, does not come out. Dissolves rock to make fertilizers. Dissolves enamel. Now, I don't drink soft drinks. I do drink orange juice, and orange juice does contain citric acid in it. But you guys, you're drinking, those of you who drink soft drinks, you're drinking something with pHs close to 3 and 4. And that doesn't mean much to you, but that's pretty acidic. Your dentist has probably already told you this, but every time you drink a soft drink, you should do what?
Drink water.
Drink water. Rinse. It's okay. You don't have to brush your teeth, but you should at least rinse your teeth with water, because if not, that acid sits there. The enamel is a base. Acid is an acid. The soft drink is an acid, so it will wear down on your enamel. Same thing goes for soft drinks. I mean, same thing goes for orange juice. Same thing goes for Sour Patch. Anything that's sour has citric acid in it. Look at this young lady. She seems to be really enjoying the lemon. That's what my youngest son was like that. He would love lemons, and he would make that face. Yeah, can I have more? He still loves Sour Patch Kids and sour candies.
I like lemon meringue pie. Have you had that?
Yes.
That's delicious.
Okay. This is the label for hydrochloric acid, a very useful acid, and of course an acid that we produce naturally in our stomach. But what is the number one acid found in U.S. industry? Yes. Sulfuric acid. And you probably smell it being used when you're going down the road and you're sniffing and you go, and then you blame the scapegoat. See, my daughter Sandra was our scapegoat. So every time we passed what on the road?
Sewer.
No, not sewer.
Paper mills.
Paper mills use sulfuric acid in order to break down the wood pulp. Okay, and the sulfuric acid is what you're smelling. Well, it's actually probably dihydrogen sulfide, but it's coming from the sulfuric acid. So when you smell that going down the highway, it is possible that it wasn't Sandra who made the noise, but it doesn't matter because we would blame Sandra anyway. So we would just, oh man, Sandra. I knew it was a paper mill, but we had fun blaming her because she would always be going, no, it wasn't me. I promise you it wasn't me. She fell for it every time. What are the characteristics of acids? Taste sour. Will react with metals to dissolve them. Will actually break them down, producing hydrogen gas from them. Neutralize bases, and perhaps you've heard the expression passing the litmus test. Okay? For example, most Republicans are known for being pro-life. They're against abortion. Okay, so a candidate would pass the litmus test if they are pro-life. Litmus, it comes from the fact that litmus is a chemical that turns red in acid and turns blue in base. So litmus can be used to determine whether it's an acid or a base. A base, like soap, is slippery. It tastes bitter. So if you've ever used foul language around your mom, maybe she made you chew on a piece of soap or something. It tastes bitter. Tastes bitter. Neutralize acids called alkaline and turns litmus blue. Blue for base. Red, acid. Red, acid. Okay, so bases are called alkaline. What are acids called? No, acids. No, it's called acids. Acids are called acids, bases are called alkaline. Okay, why? Because probably the word base is used in so many other contexts, like baseball. Okay, the part that is on the ground is usually called the base of an object. So I think in order to avoid any confusion, it's acids and alkalines, but we still know it as bases. Bases. This is interesting.
Electrolysis.
No, this is not electrolysis, but this is evidence that electricity is going through it. Okay? So this chemical has positive or negative particles that are movable. In order to conduct electricity, you must be made up of positive or negative particles that can move. And yet, this is HCl. Come on, this is A. All right, so HCl right here, that's HCl. But wait a second. HCl is non-metal. That's a molecular compound.
It's dissolved in a solution.
Yes. All acids are weird in that they are molecular, and yet when they dissolve in water, they form ions like as if they were ionic. Wow. Okay, that's the really, really neat thing about acids. All right, if given an acid-base equation, I can identify the Bronsted-Lowry acid-base, conjugate acid, and conjugate base. What does that mean? You'll see here in a second. Okay, who was the, yes?
When you dissolve an acid in water, does it split apart like an ion? Or like an ion compound?
Yes, that's what I was trying to tell you. Not, we'll talk about this tomorrow, but not necessarily to as great as an extent as ionic compounds do. But we'll talk about it tomorrow. Savante Arrhenius. I don't know quite how to pronounce this. I thought it was Arrhenius. It's Arrhenius. Okay? Basically, he found a hotel room where he heard that all the acids and bases in the universe could be found in that hotel room. But instead of having the guts to open the hotel room and walking in, he found that there was a keyhole on the door. There was a keyhole on the door, and he was satisfied to look inside. He was satisfied to look inside, which meant that he did see some acids and bases. This is what he said about them. Acids give hydrogen ions. Bases give hydroxide ions. He saw calcium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, barium hydroxide. What do they all have in common? Hydroxide. So he thought, oh, so bases give hydroxides. Okay, looking into a hotel room through the peephole meant that, did he see all the acids and bases? No. So his definition was really, really narrow. Do all acids give hydrogen ions? Actually, 95% of them do. He did not see a few of them that were around the corner. What he did not see was the vast majority of bases that were around the corner. Okay? 80% of them were around the corner. So he was way off when it came to bases. Yes?
Is this a true story? No,
His definition, I'm trying to give you a metaphor to let you understand that his definition was too narrow. He didn't see a lot of bases. According to his definition, a bunch of things that are bases, he didn't recognize as bases. Okay? The people who came up with a broader definition, who came into the hotel room, was a Dane and an English scientist by the name of Johannes Bronsted and Thomas Lowry. Bronsted-Lowry. So whenever you hear of BL or Bronsted-Lowry acids and bases, this is the definition that these guys came up with. Okay, here's their definition. Acids are proton donors or proton givers. Now in parentheses there, I told you that a proton was a hydrogen ion. That's strange. Why? Well, think about what hydrogen is.
It's a proton.
It is a proton surrounded by,
One electron.
what's hydrogen plus? So a hydrogen ion is really just a proton. Of course, why didn't Arrhenius talk about that? Because in his time, we didn't know about protons.
That hotel didn't have no protons.
That's right. Bases are not just things that give hydroxides. Bases are anything that takes a proton. The best way to imagine this is playing Frisbee. You know, Frisbee is a non-competitive sport. All you want to do is toss it back and forth. At any given moment, there is a tosser and then there is a catcher, right? If you think of the Frisbee as being an H plus or a proton, then the giver is the acid. The taker is the base. Giver, taker, giver, taker. All right, Let me give you some examples. Let's see if you can recognize who's the giver and who's the taker. Double arrows, that means
Acid base.
it's reversible.
No.
It's an equilibrium. Not really. All right, on this side, look at NH3, and who is what NH3 becomes on the other side? NH4. So what did NH3 do to become NH4 plus? Accepted an H plus. From who? Let's look at what happened to water. Okay? Water becomes OH negative. What happened to water? So the frisbee was thrown from water to ammonia. Okay? Making water what? The thrower of the frisbee, the acid, and the one who receives the frisbee is the base. But look at what happens on the other side, keeping in mind that this reaction can go backwards just like a frisbee. You can throw, receive, throw, receive, right? Goes back and forth, back and forth. On this side, you have something that has an extra H plus. On this side, you have something that has lost an H plus. So what can happen over here? So where you were a base on the other side, it became an, okay? The way to differentiate between what it becomes and what it used to be is by using a word that we have two meanings for. Conjugate. When you conjugate a verb, you're telling what tense you're dealing with, right? But conjugate comes from an original word where we get the word for conjugal visits. It's like when you're in prison and you want to spend time with your wife, that's a conjugal visit. It's referring to the partnership of husband and wife. So these guys are kind of partners. Okay, so think of it as the base and its partner, the conjugate acid. The conjugate acid. And the acid becomes, on the other side, the conjugate base. Think about it. If I throw the frisbee, then I am frisbeeless. So what can I do? When he catches it, I can receive it. So I can be an acid and be a base. Acid, base. Acid, base. What?
It doesn't make sense because I thought they all had a pH.
Well, right now, this is very superficial. We'll get deeper and deeper. Okay? How about this one?
That's the acid.
All right, Grant, thank you for volunteering. Look at what does HCO3 become on the other side? So did it give an H plus or did it take an H plus? So it is the okay, over here. Okay, what does the HCO3 negative become on the other side? Okay, so it is capable of doing what? It doesn't have an H, my friend. Gaining an H, so it makes it a conjugate. And the base becomes... Okay, this is really what they think the H plus does almost immediately upon coming in contact with water. It forms this thing called hydronium.
Heavy water.
No. Heavy water is water that contains deuterium, which is an isotope of water that has a proton and a neutron instead of just a proton. No, it's radioactive.
But what if it's not radioactive?
Wait, heavy water?
But it is, then it's not heavy water. All right, look at this.
Whatever.
Look at that. What's the significance of that?
It's crazy.
Water can act as an acid and a base. It is, we'll explain why it's neutral, but that is regardless. What does the acid become on the other side? The base, the conjugate base. What does the base become on the other side? The acid, the conjugate acid. What is a conjugate acid-base pair? It's the acid and what it becomes on the other side. It will always differ by an H and a plus. That's the difference between an acid, a conjugate acid-base pair. What are amphoteric substances? Ampho makes me remember amphibians, and the neat thing about amphibians is they can live on the ground and in water. So I wonder what amphoteric is.
They
can live in
their
their
air and around the water.
There are acids and bases at the same time.
Go, sir. Kits.
Would that be like water?
Water is an amphoteric substance. It can act as an acid and a base. One that can act as an acid and a base is an amphoteric substance. Yes?
There aren't many of those, are there?
More than you could know. Yeah. Basically, you need to have an H. Look at the characteristics. H2PO4 negative, HPO4 negative 2, HSO4 negative 1. What do they all have in common? They have an H that they can give, and they have a potential for gaining. This is missing an H, missing two H's, missing an H, missing an H. So it has the characteristics of both the potential for gaining an H and the potential for giving an H.
The Arrhenius theory of acids and bases defines an acid as a substance that releases protons in solution, and a base as a substance that releases hydroxide ions in solution. We know that ammonia can act as a base and exhibits alkaline properties, but contains no hydroxide ions. How is this possible? In this lesson, we will learn about the Bronsted-Lowry theory of acids and bases, which fills in the gaps in the Arrhenius theory. You have learned that acids are substances with a pH lower than 7. We can test for acids using universal indicator solution, or paper, which turns red or orange, all depending on the strength of the acid. Blue litmus paper also turns red in the presence of an acid. An example of an acid that you are likely familiar with is hydrochloric acid. Hydrogen chloride dissolves in water to give hydrochloric acid. Hydrogen chloride will dissociate to give a proton and a chloride ion. The proton is not just released, but it is transferred to another substance. For our example, water accepts the proton to form a hydronium ion. A hydronium ion is also known as an oxonium ion. A Bronsted-Lowry acid is a substance that releases or donates protons in solution, in our case, hydrogen chloride. A Bronsted-Lowry base is a substance that accepts protons in solutions. In our case, water. Notice that the definition of a Bronsted-Lowry acid or base is not a function of pH. So an acid-base reaction, according to the Bronsted-Lowry theory, involves the transfer of a proton from one substance to another. In the introduction, we mentioned that ammonia acts as a base even though it does not release hydroxide ions, which is stipulated in the Arrhenius theory. When ammonia dissolves in water, it accepts a proton from water. Notice that this reaction also involves a proton transfer. Can you figure out which substance is acting as an acid in this example?
Okay, so it was, what was it? NH3 plus HCl yields, was that it?
No.
We already did that.
We had already done this one?
Yeah.
All right. What do we call the quirky ion that water becomes when it acts as an acid or a base? I'm sorry, when it acts like a base? Hydronium ion. Oxonium. I had never heard that before. That's weird.
Mr. Randall, can there be an H4O?
No. I don't know. It has something to do with probably the whole makeup of it, the way the oxygen's arranged. I don't know why. Okay. Let's see. Grant, choose somebody from that side of the room to tell me whether this is an acid-base pair or not. Ruth. All right, Ruth. The way to prove it is quite easy. Make it break apart, and let's see what it becomes, what it breaks apart into. Yes. Make it give an H plus. Yes. F minus. In other words, yes, it is a conjugate acid-base pair. Ruth, find somebody on this side of the room. Max. Is this an acid-base pair?
Yes.
Okay, let's prove it. So when NH4 plus acts like an acid, what is it? What's left over?
An H plus and an H3. Minus.
That's right. You take an H and you lose a plus. All right? Choose somebody from that side of the room now.
Simone.
Is this an acid-base pair? Let's see. HCl. Make it lose an H plus. What's left over? Cl minus 1. Is that the same thing as this? That's how you do it. An acid-base pair should only differ by an H and a plus. An H and a plus. This is one H and one O, and it's missing a Cl. Wow. All right. Write the conjugate base. That means what it becomes once it loses the H and the plus. HClO4 negative. Let's see, who was the last one? Max? No, Simon. Simon. Somebody over here wants to volunteer. Who? Marie. Go. Marie. Make it lose an H and a plus. No. Just tell me what it becomes. No, not the frisbee. I don't care about the frisbee. What does it become? Make it lose an H and a plus. Yes. Good job. Marie, that side of the room. Who wants to do it? Mark, make it lose an H and a plus. Go.
4.
Sorry.
Does it have a charge?
Yes.
What charge is it?
Minus.
Folks, if you're neutral and you lose a plus, now you're negative. See that?
Wait, how's it not negative?
What?
Wait, hold on.
If you're neutral and you lose a plus,
So the two, okay, so like PO4 would technically be -3 because of the two hydrogens, it makes -1. The two hydrogens would be +2.
yes,
What if it's a negative?
then it would become even more negative. It would become less positive. All right, Lenoir.
Stew.
Bro, this one's hard.
It is hard. This is the hardest one. All right, go. Okay, let me help you with this. This is the way it looks like. Okay, the N is bonded to 3 H's, and the C is bonded to 3 H's. Okay,
So can you just take away
one of these guys is going to have to lose an H. But who? Yes, it does. Who is more likely to lose an H? Let's look at their electronegativities. Hydrogen is 2.2, carbon is 2.6, so the difference between them is 0.4. Nitrogen is 3.2, hydrogen is 2.2, so the difference is... So nitrogen is more attractive. So hydrogen's electrons are more attracted to nitrogen than they are to carbon. So which one of these is most likely to lose a hydrogen, the carbon or the nitrogen? Well, carbon is actually going to be sharing its electrons more evenly with hydrogen, so no. Nitrogen is already going to have more control over the hydrogen because nitrogen is so electronegative. See that? Because nitrogen is so electronegative, it has more control. It has more control of the electrons, which means hydrogen is more likely to be given away. All right, so what does it look like when you give it away?
CH3 and H2.
Charge?
Neutral.
Very good. That's right. Yes, Alec.
Can I go wash my hands? I put my hand in John.
Yes, Alec.
Hey, don't take more.